guys. So today I'm going to present to you our research paper, which is about improving a sequence-to-sequence NLP model using a reinforcement learning policy algorithm. The authors of this paper are me and Aboulbichr Ahmed and ouaazizi Aziza, and it will be presented by Mr. Jabri, Ismail, myself. So now we're gonna move to the plan, and we're gonna start with a simple introduction. Then we're gonna move to the problematic of sequence-to-sequence NLP model. Then we're gonna see some related work and talk about them. And then we're gonna see the proposed model to then move to experimental results and finish with a conclusion, of course. So, as you may know, NLP models are very used in customer service, marketing, productivity, and even in traveling and e-commerce, financial, legal stuff. They are very used in common daily life. So we're wanting to develop very optimized models is something we are always looking for. So creating an intelligent conversational agents remain an unresolved in the research problem that poses numerous challenges to the AI community, of course. We're still looking to develop some really natural, more optimized agents, conversational agents, of course. And the problematic with the simple, normal sequence-to-sequence model, we want our model to generate conversations that seem to be natural and more adapted and flexible. For example, here we want to ask him, where are you going? And we want him to answer us, for example, I'm going to the bathroom. And how old are you? I'm 16. Some really simple answers and really well thought. So the LSTM sequence-to-sequence model is a type of neural generation model that maximizes the likelihood of producing a response given the previous dialogue term. But on the other hand, these sequence-to-sequence models tend to generate highly generic and responses, such as we can see here. When we asked him, where are you going? He answered with, I'm going to the restroom. Then he proceeds to say, see you later, see you later, see you later, which is just generic, and that's really useful. Or it can get stuck in infinite loops and can be just repetition, which is not really good. So the proposed solution, we want a model to incorporate developer-defined rewards if it's based on reinforcement learning that are much more closely resemble the true goal of the developed chatbot, and model the long-term impact of generated responses in an ongoing dialogue. So really some of the related works which are very well known are the task-oriented conversational systems, whereas policy search has been used primarily in open-ended dialogue systems. These given chatbot systems employ unlimited action sets. Task-oriented conversation systems use finite action sets, which is not really great when you want to create natural, creative conversation. And when we move to, there is also the mutual information reward model, which uses reinforcement learning, but only one reward function. And of course, there is hyper-tuning, a sequence-to-sequence model with more data and hyperparameters. There has been a lot of papers about it. In addition to the deep reinforcement learning, sequence-to-sequence models for conversation generations are also closely related techniques, because these approaches are often trained on millions of phrases, which implies enormous computing needs, and they tend to be data hungry, although they may both be useful in the same issue. In this research, we're going to concentrate on enhancing a sequence-to-sequence model using a reinforcement learning model, employing a novel combination of reward functions, of course, leaving a potential of hyperparameters for future. So the proposed model of, as you know, the reinforcement learning has 4 or 5 elements, which is the agents. Of course, there is action A, state, and the environment. And of course, the 5th element is the reward. The reward is very, very important. As you can see here, we divided the reward into 3 sections, 3 functions, and we gathered them all into a final reward area. First one is simplicity of response reward. Second one is information flow reward. And the third one is semantic coherence reward. And of course, we used a policy gradient algorithm to just make sure that everything works in coherence and it's going well. So the proposed model has 4 main elements, as we saw: action, state, the reward, and the policy. So now an action is a dialogue utterance to generate an action A, because arbitrary length sequences can be generated. The action space is indeed limitless. So of course we have limitless memory and files, so we can't just be saving them all. State is a previous 2 dialogue terms, PI and QI denote the state. The dialogue history is then vectorized by feeding the concatenation of P and Q into an LSTM encoder model, as described by Lee and others in their article. So the reward, as we said, is divided into three small rewards, and the final reward is then getting into our model. So we're gonna now explain each reward in very, very simple terms so that everyone can understand. So the simplicity of response means, or as known as the ease of response, uses utterances with dull responses. For example, there is a list of dull responses predefined, such as "I'm not sure what you're talking about," "I have no idea," and so on, which occurs very frequently in sequence-to-sequence models of conversations. So we will give a reward. Note that the higher likelihood of a dull response equal or gives a lower reward. And here is the function of our reward function. Information flow means the semantic similarity between consecutive terms from the same agent, which will be penalized, of course. Note that the higher cosine similarity of this consecutive terms gives a lower reward. And of course, here is the function used. Semantic coherence or mutual information means the ability to avoid situations in which the generated responses are highly rewarded, but are unfortunately incorrect or incoherent. Note that lower mutual information score gives a lower reward. So when we gather them all, we get the final reward function, which is the sum of all 3 mini rewards, and we give them a probability or an importance. And since where delta 1, delta 2, and delta 3 equal to 1, we determine that delta 1 equal to 0.25. Also, delta 2 and delta 3 equals to 0.5. To complete each sentence, a reward is observed. We wanted our model to focus on getting answers which is coherent and grammatically correct. This is why we gave delta 3 0.5 or 50% of the importance. Yeah. So the policy, and here is the policy we use, which is called curriculum learning strategy. We use a curriculum learning strategy in which we start by simulating the dialogue of 2 turns and gradually increase the number of simulated terms. As the number of candidates to examine grow exponentially in the size of the candidate list, we generate no more than 5 terms, so that we can make our keep our algorithm more smooth and less memory buffering. At each step of simulation, 5 candidate responses are generated. Excellent. And now the experimental results. We evaluate our dialogue generation system using 2 automatic matrices, which are conversation length and diversity. The conversation length means the number of turns in the entire session, and the diversity we're gonna see it later. So in our paper today, we will compare 3 approaches, which is supervised learning for sequence-to-sequence model, the semantic coherence for pre-training a policy model, and the dialogue simulation between 2 agents, which is based on our RL model. The dataset we used has 10 million conversations from open subtitles, and we omitted 0.8 million sequences because they had a high probability of generating a response such as I don't know what you're talking about, which are dull responses. We don't want our model to give us dull responses. So the model evaluation. It is in fact difficult to evaluate the dialogue system. Metrics such as clue and perplexity has been really broadly used for evaluating the dialogue quality. But in our research paper, we do not use clue or perplexity for evaluation because the goal of our proposed system is not to predict the high probability of response, but rather the long-term success of a dialogue and its diversity. So we use the length of conversation. Length of conversation means the length of simulated dialogue. It is the first metric we propose. When one agent starts producing dull responses, such as I don't know, we say the dialogue has come to an end. And here you can see the model. The model sequence to sequence has 2.76 simulated turns, and semantic coherence model has 3.54, and our proposed model has performed the best, which is 4.63 of simulated turns. Of course, this is just the average number of simulated turns from all the 3 models. And for the diversity, the number of distinct unigrams and bigrams in generated responses is used to calculate the degree of the diversity. As you can see here, sequence-to-sequence model and the semantic coherence model performed a bit more well than our model in the unigram. But since, as I said, since we don't want our model to give us dull responses, unigrams such as okay or fine, we want long-term success conversation, which means diagrams are much more important in our case. And as you can see, our model performed very well compared to the other models. So we have 0.044 diagrams compared to the others. So as a conclusion and future work, our proposed model was successful in generating conversation responses that maximize future rewards and demonstrate global properties of conversation. In the future, the proposed model could be extended with additional hyperparameters, additional rewards, and performance metrics to address a wider range of human-computer interaction tasks, particularly those with long-term dependencies and delayed rewards. This could result in conversations that are much more beneficial to the users, of course. And thank you for your attention. And let me know if you have any questions. I will be more than happy to answer you.